The final frontier speaker, I like that. Yeah. All right. So in a few years, men will be able to communicate more effectively through a machine than face-to-face. So this was the opening sentence in a paper written titled The Computer as a Communication Device by Licklider and Bob Taylor. In this paper, they argued that the true potential of computing and computer science isn't to help us process data or to give us access to data, but rather the true potential of computing is to help us communicate better with one another. And what's remarkable about this, this statement and this paper is that it was written in 1968. So obviously, some 50 years later, this prophecy hasn't come true, right? We're all here at SIGGRAPH, traveled great distances to meet each other face to face. But the statement and the thought is as prophetic and relevant today as it was 50 years ago. And what I want to do in this talk is convince you, hopefully, that this is, in fact, an important frontier, maybe the final frontier of computing. All right. So humans are social animals. This is self-evidently true, but if you don't believe it, there's a lot of research that tells us that our health, our happiness, and even our productivity as workers is dependent on how well we socialize with other people and partners. And our perceptual systems, our eyes, our ears, our brain, in fact, is optimized. It's incredibly sensitive to picking up subtle details of how you move, how you speak, and this is, of course, well known in this community. The main obstacle, or one of the main obstacles at least, to communication is and always has been distance. Many of you, myself included, don't live where we grew up. Right? We all have this experience of relationships which we leave behind when we move on to new places. And even if you yourself still live where you grew up, you know about friends and family that have left. And it's a truism that we all know that proximity determines relationships. You have relationships with who you are close to. And it's why there's been a kind of technological progress from the Postal Service, where we could just have sort of some information exchange even if you are further away. To in the 1800s, there was the innovation of the Morse code. And for the very first time, even over great distances, you could still communicate some elements of information that you wanted to. But it was very much limited because it didn't have all of that context that's really important in connecting with another person and communicating with them. The next big breakthrough, as we all know, was the telephone. And this allowed for the first time for some of that, contextual information, some of that, the tone, the prosody of what you say, how you say it, to be communicated in real time. And this was a real change for humanity. And then finally, like in the 1950s, conferencing emerged, right, where you could actually see the other person, and now you had a window with vision to see it. Obviously, that's an iPhone, which wasn't available in the 1950s, but yes, the technology was. Yeah. So what's next, right? Why is it that, despite the fact that video conferencing exists, we all choose to come over here? We choose to, fly over people for job interviews. We choose to fly back home to meet family. What is it about video conferencing, even as a solution as it is today, that is fundamentally limited and it doesn't fulfill the vision of Licklider and Bob Taylor? I think there are many reasons, but, a few obvious ones is what I would call social signal interference, right? One is that when you talk to someone else, you want to feel like you're engaged with them, right? You want to look at them in the eyes. You want to really feel like they're observing you, you're observing them. Of course, in practice, it looks more like that, right? You're looking down at the screen instead of looking at the person. And this is a kind of a small example, but this is one example of where the technology itself interacts with what you really want to do, which is talk to the other person as if they're really there with you. The other example is, of course, the tiling that we've all seen when you have large groups of people. You see the center one. There are a bunch of people over here. There's a separation between you and the crowd. And as there are more people who join, you can see they sort of tile and they become smaller and smaller. And it's harder to see what they're doing, how their hands are gesticulating, how their body language is moving. I'm not sure why this person is seems to be in the middle of an ocean conferencing, but it's probably a concept to mention. So this is kind of, I think, one category of interference. And in fact, in the paper themselves, they noted a much deeper and more interesting reason why video conferencing is limited, even anticipating back then. They called it externalized models. And when they say models, they mean mental models, right? That they say that in order to communicate well, I have a mental model, you have a mental model, and it helps to externalize how I'm thinking about something in some sort of artifact in your space that you share and you are aware of as well. So we can point to it. And in the absence of this, and this really rings true to me, in the absence of this in video conferencing, we often make speeches at each other. Whereas in person, it's often we refer to these common artifacts, these externalized models of ours. And they say that perhaps the reason present-day two-way communication falls so far short of face-to-face communication is simply that it fails to provide facilities for externalized models. We're not there in the same space with the other people. And this is kind of like the fundamental, in my view, one of the fundamental reasons why video conferencing is not the same thing as meeting a person face-to-face. In the last couple of years, there's been, like a big change. 3D displays for artificial reality have really become consumer items, right? We've seen the Oculus Rift, Sony, Vive, Google Daydream. All of these devices have come out with VR displays. And then Microsoft and Magic Leap have come out with these consumer, or let's say quasi-consumer AR devices as well, right? And so this has been a big change in the last couple of years, and it really presents an opportunity, perhaps for the first time in a long time, to revisit this statement by Licklider and Taylor. And so I think it's now timely to restate this today in 2019 as another kind of a vision for what research should be like, not just in computer science, but particularly in computer graphics. So where a lot of us are academics, so I'm sure everyone's itching with their pens to make a slight edit. I will make it too. There we go. In a few years, people will be able to communicate more effectively through a machine than face-to-face. So what's the challenge in doing this? The goal itself is to enable authentic communication in this kind of artificial reality. And the challenge is actually, it's in this sentence itself. There's a contradiction in this sentence. You can see the two operative words, authentic and artificial. And these are opposites of each other. These are contradictions, right? And we've seen some efforts at getting social VR into, social communication into VR, and sometimes even in AR. And they often look something like this, right? There are these stylized avatars, and they work well if you want to interact with somebody for something where the social interaction isn't actually the objective of the interaction. It's gaming, something of the sort, right? But it has failed to replace in any significant way video conferencing, talking on the phone. It has failed to displace that in any sort of significant way. And so if I have a thesis for this talk, it is that metric telepresence is sufficient for authentic communication. And what do I mean by metric telepresence? What I mean is that we want to represent the true interaction as it would happen if the two people were face-to-face. Not perceptually plausible, but what actually happened. It should be indistinguishable from a real interaction, and it should replicate, to the extent that we are able to, what the two people would have done had they been in the space together. So distance should quite literally melt away. And so this, I say here, sufficient. I truly believe, actually, that the stronger version of this thesis is also true, that it is necessary for authentic communication. And as we develop this, I'll explain why I feel so. So a good place to start is, what is the state of the art in telepresence, right? Probably one of the earlier works in this is in 1997 by Takeo Kanade at Carnegie Mellon. They built what they call the virtualized reality system. And this was 51 cameras back in the day when cameras were analog. You had to record them with video cassette players, recorders, sorry. And they showed that you could actually reconstruct multiple people interacting and then replay them in 3 dimensions as well. Almost a decade later, Professor Rosina Bashi at Berkeley demonstrated the real-time systems with markered motion capture and cameras as well. And this was really like the first demonstrations of actually experiencing this in real time. But the real kind of recent breakthrough showing that this could actually be something serious and present was in 2016 by Shahram Izadi and his group, then at Microsoft, now at Google, in showing this sort of reconstruction in real time through the HoloLens system too. Now, this sort of body of work is what I sometimes refer to as measurement heavy and model light, meaning that there were 51 cameras used in the leftmost system. There were a bunch of cameras used here. This one used 12 stereo pairs as well. But it was a real-time system and a real kind of accomplishment. In contrast to this body of work, there's been an effort. So a couple of years ago at SIGGRAPH, there was a really exciting demo called the Meet Mike demo by the WikiHuman team, which was a real kind of accomplishment of engineering and research collaborations between USC, Disney Research, Pixar, Cubic Motion, and other companies. And then it was developed. Some of that technology was used in a development last year, Siren by Epic Games, and then more recently, Digital Doug by Digital Domain as well. So in each of these, you can see like a progression of realism. And the work that we do at FRL, Facebook Reality Labs, is along this line of research, and here's where we are. So this was research we published last year at SIGGRAPH, and I'll play some of the videos.
There's this big, ugly sucker at the door, and he said, "Who do you think you are, Lena Horne?" And I said, "No, but that I knew Miss Horne, like a sister, and she told me next time I was in town to come and look her up." Well, next thing you know, it was Lena this and Arnold that, and oh, have you met the Duke? He's right over there. And that club was jumping and jiving. Ooh, that sounds good.
So this is, in fact, a parameterized model, and these are renders inside our system as well. And so this is something which we call codec avatars that we've been working on for the last few years. You can see like a progression of models ending up with Nadia's model over here, which you'll see in a second is actually a mesh which is rendered. And what we want to use these avatars for is in a real-time communication experience, right? Something like this one, which we also showed some early results in that 2018 paper, where you have two people who are wearing these headsets. Now, obviously, because they're wearing the headsets, you don't have a clear view of their face, but they can actually interact, as you'll see in this short clip.
The hidden code itself, and
Yes.
it's not getting any features from the generated texture.
From the generated what?
The texture that's generated at the end.
Well, I mean, they both come from the same source.
I see.
They have the same latent variable that informs how they should generate these two components, but they don't share any components, at least in the V0 architecture.
So you're probably wondering what the dots are about. They're just there for, they're not really used. But one of the things which I like about this clip is, in the middle of the conversation, Shui below, he says something, and Jason above, he leans in and says the generated what? As if leaning in the VR space will help him hear better what Shui said. Obviously it doesn't, but the illusion was real enough that he wanted to convey that information, and it seemed to be captured well. So this sort of gives us a rough sketch of what sorts of challenges we want to cover in the research space of telepresence, metric telepresence. The first one is
the hidden code itself, and
Yes.
it's not getting any features from the generated texture.
Sorry.
From the generated what?
The texture that's generated at the end.
Well, I mean, they both come from the same source.
I see.
They have the same
have to
latent
suffer through
variable
this.
that informs how they should generate these two components, but they don't share any components, at least in the V0 architecture.
So the first is metric identity, right? So video conference is something which you can just walk up and start using with someone. The question is, how do we build these avatars for 1 billion people, for 7.5 billion people? What is the process that lets us do that in a lightweight way? And it shouldn't just look like them, right? Which may not be that hard. You can do a scan, it's not hard to do that. How can we make it move like them? How can we make it sound like them? How can we make it sort of look in the same way they do? So this is kind of one sort of category of question. How do we get identity-preserving avatars? The second one is metric behavior. with impoverished sensing, like without having something which is, a room full of cameras and sensors, how do we actually reproduce the behavior of a person so that their loved ones, their family, their friends, their professional colleagues recognize that that person is moving the way that you expect them to, right? And then finally, it has to be done instantly. So in the special effects industry, we've seen there's been success in getting realism and to capture the essence of actors on screens. But oftentimes, this requires like hours of rendering per frame. It requires intervention from artists and input from them as well. And on the other hand, we have games in which sometimes this sort of realism is eschewed for performance. But in this case, we actually need to get the full gamut of a person's behavior, like the tails of the sorts of things they do, and to be able to do all of that in real time. So I think one difference of telepresence, particularly compared to games and special effects, is in this case, the objective is communication, right? This is, in fact, in the intellectual tradition of a telephone, video conferencing, this is a communication system we're building. And therefore, reconstructing the signal, in other words, metric telepresence, reconstructing the signal I want to transmit in its full bandwidth is what the space requires. And so this is kind of like a simplified illustration where you have two people separated by a distance. And what you have to design in this space are sensors that can actually sense what the person is doing, an encoder that takes that sensor, compresses it in some sort of form that captures the behavior that that person is doing, transmits it over the network, and then a decoder that takes that representation and decodes it, or in the graphics view renders it to a display that we want to show to the other viewer. And then this is a cycle that continues. For reasons that I'll explain shortly, this decoder is actually curious in the sense that it actually depends on the encoding of the viewer, right? So it is not purely a function of what the person did, it's also a function of what the person who's viewing it sees. And then finally, the group has to be in a shared environment of some sort. They have to feel like they're in the same space together, even though they're in different places on one end. And this problem becomes quite severe with AR, even though it's a problem in VR as well. I won't speak too much about the circly arrows, but that's in fact another important research direction on how the system has to be a memory-based system, not a memory-less system. And so codec avatars and this general concept of telepresence, which is one way of looking at this problem, is in fact a pair of functions. A codec avatar is a pair of functions, an encoder on one side and a decoder on the other side, right? And the encoder takes in the behavior of the person, produces some parameterized representation of it, and the decoder takes that representation and produces a realistic avatar that the other person sees. So let's look at both of these functions in isolation. First, let's look at the outside of this, more of what we would probably think of as the graphics problem. If you're given some sort of representation of the person, how do you produce what the person should perceive, right? And there is in fact a history in the community of this, right? So metric avatars, there was the breakthrough work in 1999. Like this is one of those prophetic works that was decades ahead of its time by Blanz and Vetter that produced this sort of linear model that could span the space of shapes and appearance. And shortly after that, active appearance models also continued in that kind of work. And most recently, some of the work by Tabo and Derek on this sort of representation of realistic avatars too. But in this sense, this decoder is a function that takes in parameterized form of the person's behavior, in this case, this code, and also the code of the person who's viewing it, and produces the left and right view that the person sees. This is kind of, I'll explain why the structure looks like this in a second, but it's part of what is probably more general, which is that you want to take what the person did, not just how they look, but also how they sound, not just what the other person sees, but also what the environment is, and then produce what the viewer should see with their left and right eye and what the viewer should hear as well. So this problem, a person's behavior is not just visual. This space requires actually research into 3D spatialized audio, HRTFs, that space of research as well. So in a very general sense, what we think of this as is we have a parameterization where it's just a vector of 128 or 256 numbers that captures what the person is doing. One version of this, perhaps an earlier version, would have been blend shape coefficients or PCA coefficients in a linear sense. But of course, these days we have compositional functions, deep learning networks, that can take this kind of a function and produce the mesh. Where here now this vector is in fact the concatenated XYZ coordinates of this mesh over time. Now, an observation, of course, that is known in the field is that, in fact, the appearance depends on your expression as well, right? Or your gesture. So if you look at this neutral expression, as the person makes a scrunched up face, you can see blood rushing into the forehead region, the temple region, and that changes the appearance of this person as well. So it's that same code that represents the geometry as well as the texture of this person, right? And so you can think of this in this form, that you have this number which varies, and as it varies, it changes not just the geometry, but it changes the texture as well. So I'll play that quickly. This is, of course, an unwrapped UV map of the geometry. And now this shared code is used to then render an image. And here's where the concept of metric telepresence comes in, as a concept that informs some of this work, right? So what we have over here is we train these networks to reproduce the images that would be actually observed. So you see over here this swiping line that's between the true video that's taken and the image and the render of this model as well. And so in this sense, it is a metric telepresence model. You directly minimize what the sensor sees, and you train the network directly to do that. And just as we've seen previously with PCA coefficients or blend shapes, these codes also have a similar, maybe interpretation, if one wants to call it that, right? You can see these are what the different codes mean. If you tweak one of them while keeping everything else to neutral, this is what they look like. So that's probably what that value looks like. And for those of you used to seeing something like this, you can observe something that's different from what you usually see when you see PCA coefficients sort of varying to plus minus sigma. There's non-linearity and asymmetry in the way these are transforming, right? And that's interesting. So I had mentioned earlier that there is some sort of effect of the viewer on the images that you see. And this is also something that should be kind of familiar to this audience, right? When you see a face, in this case, from many different viewpoints, obviously the texture is different because of the reflectance properties of materials. And over here, as you see on the nose of this person, when you look at it from the left at grazing angles, the skin collects light from all sorts of directions and then accumulates it, sends it out. You can see a single lobe on the nose of the person, and as you go into the center, it breaks out into two. So where the viewer looks at the model from changes what sort of appearance it sees, or he or she sees, right? So that's why this function that decodes it in a rendering sense depends, which is again familiar, not only on the state of the object, but also on the state of the viewer. And so once again, in this kind of view, you simply augment it with a code that encodes me, the viewer's position or behavior. And if you note one sort of structure here is that this only influences the appearance and not the geometry. Where I look at you doesn't change your geometry. So it exclusively impacts the texture. And then once again, you render the image and minimize it according to the same program. And now let's see what that looks like. So here the geometry is shared. It doesn't change according to view, but each viewpoint actually produces a different texture. And as you see over here, each of these textures is in fact different. And the parts where you see darkness, the death and decay, those are not visible in the individual views. So networks, being famously lazy, don't bother to impute over there. They restrict their capacity to the parts you'll actually see. And so now you can sort of see this a little bit more end-to-end. If over here what we're doing is we're playing a sequence of codes and then tweaking the viewpoint. So it's looking at it from different viewpoints. And you'll see that the texture changes, the geometry remains roughly constant, and the images at the end are obviously changing. But it captures some of that illumination effect. Now, one of the attributes of these deep learning methods is that they're very data hungry, famously hungry. And to feed the beast, we built a system called Bugsy. So this is the system. It has about 100 microphones, which we're not going to talk about much in this presentation. 160 cameras. These are these are 4K cameras, actually 11 megapixels capturing at 90 hertz, and 450 lights, right? So it produces a lot of data. It looks something like this.
Hi, my name is Steve Lombardi. For those that don't know me, I'm a researcher at the Pittsburgh lab working on codec avatars. The goal of our work in Pittsburgh is to create a system that enables social experiences in VR and AR just as you would have them in real life. When Yasser asked me to do the symposium talk, I thought, great, I'll let my avatar speak while I just sit on the couch. But I was told that I should probably show up, so please welcome Real Steve.
There's no Real Steve, sorry. Well, actually, he might be here. Okay. So what you're seeing over here is actually a sampling of view, right? But dynamically as well. So the attribute is that we actually have video sampling, temporal sampling of a dynamic object plus the viewpoint, and then as I'll show, some early progress on lighting too. What can we do with this, right? So this is an example of reconstructions. These are frame-by-frame multi-view reconstructions. So there's no photometry used. There's no temporal tracking, nothing. These are frame-by-frame reconstructions, right? And then, of course, we track them. And to give you a sense of the precision of tracking, sort of like zoomed into one part of the person's face. And each of these are obviously here. You can, just to evaluate the quality of this, just pick a vertex and track it. And you'll see it seems to be good. And so from data from this, a person sits in, makes funny faces for a few hours, as we often do in these sort of devices. They get captured. The input images get reconstructed. Then key point detection for different points on the face, which has also recently become much more robust. You track it precisely, and then using a PCA basis, you track it one more time. And then finally, you learn this codec avatar from it. And here what I'm showing is, once again, this concept of metric telepresence. So you have on the right the true image, and on the left the rendered image, and there's a line with a white sort of separator that's sweeping through. After a while, that line is going to fade out, and you can evaluate whether it seems like if you can see the line clearly, then or the more clearly you can see the line, the worse the result is, right? You'll see the line will disappear, but it's still sweeping. When it gets to extremities, you can see when the background is shown a bit, you can see the video versus the true thing, right? And this is all generated from that parameterization. Okay. So this is kind of like one instantiation of what this decoder could be, right? What could take a parameterization and produce the images that a person sees to make it indistinguishable from what the person's actually doing. So that's one half of this of the story. The other half is, how do you actually sense in real time what the person is doing, and then figure out what this code is. I should make a note that what I just described is probably a simplified version of what we actually do. It is, in fact, a simplified version of what we actually do. And to see the full detail of it, I would, of course, refer you to the papers, which I will have a list of at the end. So what is the encoder function here? What is the function that takes in what the person's actually doing and produces this code, right? And so here there's a question of hardware design, right? How do we actually get a full sensing in a way which is not obstructive, which is not overwhelming for people to actually use? And of course, vision is part of the story, right? This is, in some sense, a machine vision problem. But audio is obviously a very strong cue as well. And increasingly over the past years, there have been other sort of modalities that have emerged as good sensing modalities for human behavior. And it's largely unexplored to see how, not just what those modalities are, but even on regular ones like video and audio, how can we fuse this information through temporal modeling and those sorts of ideas to figure out what a person is doing on power budgets, on heat budgets as well. So this is, I think, another very rich area of research that's unexplored. And of course, the challenge in VR at least, and to a degree in AR as well, is that the face itself is occluded. So you can see over here in a two-way conversation, the face is occluded. So I'll show you what as you had seen earlier, what a clip looks like.
So I was telling you that I believe in ghosts, and you don't because you believe in science.
Yeah.
So I think I watched too many ghost stories.
So you can see over here, having a camera looking out at you is not going to help you that much, right? Because you still have to guess what the person's doing underneath. And that's one of the reasons why this other challenge of metric behavior, figuring out what a person is doing with minimal sensing, is really one of the core challenges over here. You have to give the system a computational equivalence of imagination. Like coming from pieces, a jigsaw puzzle of sensing, can it actually impute what a person is doing? Like with their feet, with contact, those kind of things. So this is another, I think, an interesting and important, the inference part of what a person is doing. And a number of the demos that we've seen, for instance, the Meet Mike demo, it was in fact an asymmetric experience, right? It's only one side of this interaction that could actually see something in VR, see the other person in VR. The other side, Mike himself, had a camera looking at his face. And it's similar with the Siren demo, and also most recently with the Digital Doug demo as well. Probably the pioneering work in this area was published a couple of years ago at SIGGRAPH as well by Hao Li and his colleagues, also from Oculus. And this is a demo of their system. You can see they can track facial expressions here on this model. And there was some important work, probably the first photorealistic results shown by Christian Theobald and Matthias's groups in Germany.
We present Face VR, a novel method for facial reenactment in virtual reality.
We present Face VR, a novel method for facial reenactment in virtual reality.
So very exciting progress.
This is a virtual
Justus,
avatar.
the first author of the work as well.
I'm very.
And here's some of the results that we've produced in the last couple of years. You can see that same sequence they started showing earlier.
So I was telling you that I believe in ghosts, and you don't because you believe in science.
Yeah.
So I think I watched too many ghost stories. I used to come home from school and watch Are You Afraid of the Dark? Every day. Did you ever watch that show?
Yeah, I watched it a couple times. I think I read some of the books too.
They had books?
Wasn't it? No,
Is that
I'm thinking of
Goosebumps?
Goosebumps. I'm thinking
Yeah.
of Goosebumps.
Did you watch that movie? They made the Goosebumps movie with, what's his name, a couple of years ago? That was weird.
I didn't see it.
Yeah. But I would come home and watch it by myself. I would turn on, like, it would be my treat
The
before
ghost
homework.
is taking over. Oh, no.
And I would watch Are You...
All right, okay. They go on and on. Okay. All right, so what is the challenge? So one of the things we did is we designed this headset, this modification to the headset, where we added 4 cameras, one looking at the mouth, 2 looking at the eyes, and 1 looking at the glabella region of the head. And what you see is that this sort of jigsaw puzzle look of the face. And the challenge is, how do we go from these views to what the code itself actually is? Because once we have the code, we know we can render reasonable looking renders of the person's face. The problem is there is a domain gap. And this is a somewhat subtle problem that's hard to describe, but I'll make an attempt at it. The way machine learning algorithms work well is if you give them input-output pairs. If I show you this, produce this for me. If I show you that, produce this for me. And you give it a lot of examples of these input-output pairs, corresponded pairs, and it learns a regression function across them or a classification function across them. The challenge over here is that we have a large bag of input. We can record a lot of data from the headset. And we can also produce a lot of codes in Bugsy or other multi-view systems. What we don't have is correspondence between them. Once a person wears a headset, we have the input images, but we have no way of ground truthing what the person's actually doing. And so even though you have these 2 bags, you don't have the correspondence in them. And this is sometimes referred to in the community as the domain gap problem, right? And so the input-output pairs don't exist. So what do we do? Once again, we look at a recent innovation in the computer vision community called style transfer, which uses GANs to transform what are IR images over there to RGB or visible spectrum images here, right? I won't go into details. Once again, if you're interested, please do refer to the paper. And what we do is, in fact, I find these to be interesting videos because they visualize gradient descent on a face, which is awesome. And what you see here is you have a particular view. So you take the code, you condition it by the view that you want, which is very close to the eye. And you take the actual images that you see, and you transform them into RGB using the style transfer system that I just mentioned before. And what you get is you have this differentiable renderer that produces the image. And what you want to do is you want to tweak this code. If you tweak the code, the renderer will produce a different state of the face. And you want to minimize the error, the pixel by pixel error between what the code thinks it's seeing and what the sensor itself saw, right? And what you'll see over here is as I play the movie, we'll compute a loss. What's shown over there is actually the pixel by pixel error across all of the different cameras that we have on the headset. And we'll tweak this through gradient descent. So it'll search in this latent space for faces, and it'll minimize that error. And what you should observe up there is, does that expression match what you think the person should be doing in that? That's the game. Okay? So I'll play it. Let's play it first. And you see, first thing to look at is the loss. It minimizes over time. So let me play that one more time. And this time, look up there. As this thing moves, you see she closes her eyes and adjusts her mouth. Play it one more time, and now you can see it over here because it's being rendered. She closes her eyes and her mouth. I think this is nice, so I'm going to show you a few more examples. So we'll just play them. She changes her expression. That's another example. And if you notice, all of these are initialized from neutral. I'd like to point out once again, conceptually, what we're attempting to do is explain the observations as they are. We're not making appeals to plausibility. We're attempting to reproduce what the pixels see. And one way of seeing this, once again, with this concept of sliding, is we're sliding what the actual cameras see, and then the renders on those views as well. So I'll let this play for a while. Yeah. And so now we have these two functions, the encoder that we talked about and the decoder, and we can put them together, right? So the encoder takes these views from the camera, transforms them into this latent representation, a code, a set of numbers that describes what state the avatar is in. The viewer views this, right? That's the view. And then it decodes it into the texture and the geometry, and then it's finally rendered in the view of the person. And so this is the entire kind of like machine working end to end. As you see it. The person changes their view, a code is estimated, the geometry and texture is produced, and then you can see the person's final image. And so this is the system working in real time. You can see a bit of lag, but it's worth mentioning that it's a very different thing to see this on the screen and actually see it in VR when the person is there physically in 3D with you, right? So it's a very different experience, and one I hope we can all experience soon. So in one sense, the reason why we have this kind of architecture of going from images to a compressed code is to help the neural network learn something. As a scientist, I think it's very interesting, always very satisfying when you choose a representation or make a design choice because of one criteria, and it turns out to be informative or useful from a completely different direction. And in this sense, the compressed representation is useful as a network compression, right? You send this over the network, you want a compressed representation, you natively have one now. And that's kind of appealing. And so let's look at some results, right? So what can the faces do? Well, what can your face do? Can you show us?
Well, I've always hoped you would ask me that question. So I have some pretty good, I think, mouth movement.
How about your eyes? Can you look left, right, up, down? Good.
Yeah, I can do surprise. Ooh. I think one of my favorites is puffing my cheeks.
The mouthwash commercial.
And rolling my tongue.
That's pretty good, actually.
Yeah.
Good.
Yeah, not a lot of people can do that.
Yeah, one sort of good test is, can we get through like the first few letters of the alphabet? A, B, C, D. That usually shows what is and isn't working.
B, C, D, E, F, G.
Good. P is a good one.
P, all the plosives.
Yeah. The plosives. Pa, yes. Pa, A, B, C. So you can see. All right. And so here's another one.
Have you told anybody about Yahtzee yet?
What's Yahtzee?
That's where we build a yacht and then we collect data on a yacht.
Oh, that's so clever. I like it. We should definitely do that. Now we must do that.
I think we can trademark it.
We have to. Yes. Okay. We're not going to do And then finally, it's worth seeing, it's good to show a couple of examples and see, but we're still quite far off from actually making this work in all sorts of circumstances. The distribution of things that we do, it's a very long-tail distribution. And so here's an example. I thought I'd share it just in the academic interest of saying we are actually far away from making this work in all cases. So, I wonder if we should avoid laughing because laughing looks so creepy.
Or evil laughter. Maybe we should.
Evil laughter.
Yeah.
We'll get Stephen next time. How about that?
Yeah, that's great.
Yeah, so I mean, there's some ways to go there. All right. So I'll show like a quick overview of like where I think this one organization of this space, right? Two-dimensional organizations are usually helpful. So what are the two kind of principal directions where we need a lot of research and progress? One is scale. Right? So currently, this is a personalized model. You have to sit in the capture system, that big capture system, for hours to get a model that's just specialized to you. And that's really not something that's going to work as we try to get this to people to use in the wild. Right? So that's one kind of direction, and how do we build universal faces? The other one is completeness. As nice as floating heads are, they're not the same thing as meeting a person. You really want to to feel like you're in their presence, to share that space with them. You need to see hands, you need to see the body, you need to see the rest of the environment. So completeness is the second axis. And that's kind of like complete avatars is what we want. And ultimately, there's this whole space together with them. What this doesn't include are things like quality, optimization, hardware. There are lots of other axes, of course, as well, but these are two. And along the line of scale, of course, there has been a lot of interesting work in the past, once again by Blanz and Vetter, the work by Angelov et al. To try to come up with some sort of a space of bodies that's been developed in the last couple of years by Michael Black and his group at MPI. And so we're also working on this, trying to collect a repository of high-quality human faces. And we're very proud of having the largest repository of 3D teeth as well. Annotations for them there, detail. And we're starting to build large-scale models of people of this sort as well. So you can see. So identity, this is what I had mentioned about how do you actually build lightweight models of people. And I think one of the most important things is to build this universal human prior. To figure out how to do this from small, impoverished data sets you can collect of the person, of an individual, through a cell phone or through a short capture. The other direction is completeness. And there's a kind of, like a long history over the last couple of decades of building these large multi-view systems around the world. There are some in Kyoto, in China, in Germany, in the US, obviously. And so it's really interesting that this is not just that this is an international phenomenon to try to understand movement in humans, but also the fact that each one of these systems is still active. Like it really is a subject of ongoing research. I'll just skip a few slides here. I think it's not that relevant. This is the system we've built to try to capture full bodies. The system, the things that you saw inside were microphones, because really we need to start thinking about humans not just as visual creatures, but audio creatures as well, and these things have to be learned jointly and represented jointly. So some early results on reconstructing humans, right? So this is a reconstruction. There's a full pipeline that we have to develop, which...
I'm standing in the Sociopticon, a dome containing 180 cameras, 1,600 microphones capturing about 100...
Quickly, we have to do segmentation, key point detection, tracking. The entire pipeline has to be re-engineered for bodies, and things are starting to look interesting. And just to be clear, this is in fact a fully corresponded standard parametric model with facial expressions, hand gestures as well, without markers. And we can start to see some early results on what this could look like. There are obviously significant artifacts here, but this is, I think, one large open area of how do we actually get full body movement and acoustics together, so behavior. Hair is another important part of identity, or so I'm told. And you can see this is strand by strand accurate. This was work that we published this year at CVPR, as you see up here. This is one sort of promising direction of research. Some work that was published at this SIGGRAPH, presented a couple of years ago, 2 days ago by Stephen. This is an example of results, different hair types, so on and so forth. I'll skip this.
Hi, my name is Steve Lombardi. For those that don't know me, I'm a researcher at the Pittsburgh lab working on codec avatars. The goal of our work in Pittsburgh is to create a system that enables social experiences in VR and AR just as you would have them in real life. When Yasser asked me to do the symposium talk, I thought, great, I'll let my avatar speak while I just sit on the couch. But I was told that I should probably show up. So please welcome Real Steve.
Last aspect of this is, what about environments, right? Objects in the environment. When you want to share that space and actually interact with those externalized mental models, you have to have some representation of the environment around you. And there's been sort of pioneering work that's been done over the last 2 decades by Paul Debovic and his colleagues in trying to see how can you relight humans to make them feel like they're in an environment. And we're also, of course, getting some early results in this space as well. So in conclusion, so these are kind of two directions, right? And finally, all of this has to be done in real time. I think this is another challenge which then spans systems research as well as just the inferences and the rendering communities too. So to conclude, when most people think of AR and VR, they think of it as yet another technology in a line of technologies that are designed to separate us from the world around us. But I think this view is profoundly mistaken. Done right, if we are actually able to build a true metric telepresence system, it will connect us to our friends, our loved ones, our colleagues in ways we've never seen before. And telepresence, I think, is the next step in this. Beyond just building relationships between people, I'll end with also a quote by Licklider and Bob Taylor in that same paper where they wrote that when minds interact, new ideas emerge. And I think the value of that, to be able to connect lots of people who would never talk to one another or not be able to, really ideate together, that idea is extremely powerful, and I'm really excited about the possibilities. So this has obviously been work in collaboration with, some of the work I've shown you is collaboration with my team, which it's a privilege to work with. These are some papers, and I'm happy to take questions. Thank you.